Technical difficulties. I'm very pleased to invite Moshe Vardi, who actually doesn't need an introduction, but he has a long list of awards which I would like to tell you briefly about.
Make it short.
Okay. Moshe Vardi is University Professor and the George Distinguished Service Professor in Computational Engineering at Rice University. His research focuses on the interface of mathematical logic and computation, including database theory, hardware-software code design and verification, multi-agent systems, and constraint satisfaction. And he's the recipient of numerous awards, including the ACM SIGAX Gödel Prize, the ACM Analogously Award, the ACM Sigma Quad Award, the Knut Prize, the IEEE Computer Science Society Good Award. Okay, actually, what he has to talk today is going to be interest to a lot of people here. So, without further ado, Moshe, all yours.
Thank you. It's a pleasure to be here. Before we solve the AGI problem, I'd like to get to the computer start presentation. And let's see if we can do that. So today I'd like to ask this somewhat rhetorical question: what is theoretical computer science? And this is meant to be a provocative talk. Everybody say, oh yeah, I told you, and I have not done my job properly. And I would welcome a vigorous discussion as we get to the end. In the middle, feel free to ask questions for clarification, but say opinionated discussion today. So, kind of the starting point was identity crisis. So, I think of myself as a computer science theoretician or a theorist, some people say. But in October of 24, I looked at Wikipedia, and it described me as an Israeli mathematician and computer scientist. I said, am I a mathematician? It wasn't quite clear. So I went to Wikipedia to ask, what is theoretical computer science? And it says theoretical computer science is a subfield of computer science and mathematics that focus on the abstract and mathematical foundation of computation. So yes, abstract, I agree, mathematical, I agree, but to say it's a subfield of mathematics, there I have somewhat of a disagreement. But it's not only Wikipedia. In 2019, our neighbor here, Avi Wittgenstein, that gave absolutely beautiful mathematical talk this morning, wrote a book, beautiful book, called Mathematics and Computation. And he described, he said, the theory of computation is the study of formal foundation of computer science and technology. Perfectly, I'm perfectly okay with it. The scope is mostly around computational complexity, computational learning theory, cryptography. There is a classification of computer science theory into volume A and volume B, based on the handbook that was published in 1990, but it comes from some terminology. Volume A is algorithms and complexity. Volume B is logic, semantics, automata, things like that. And none of that is covered by Avi's book, which is legitimate, okay? It's his view of theoretical computer science. And the book is lovely. But the title, the mathematical computation, again seems to suggest that Avi thinks that theoretical computer science is part of mathematics. And that's the question that I'd like to discuss today. Is TCS, is it part of math? Now, one way to look at it is sociological. So there is a famous kind of say, what is mathematics? That's what mathematicians do. It's very hard to define mathematics. To say mathematics is whatever mathematicians do. So that means now what is a mathematician? You have to be in a math department to be called a mathematician. So how many computer science theoreticians have a position in math departments? Okay, but Avi is a great mathematician. There's no question about it. He received the Abel Prize, he's in the math department. Okay. But the answer is, I was thinking, okay, I came to Rice in 1993, I applied for a job. If I had applied to the math department at Rice, would they have given me a job? The answer is no way. They would look at me and say, where is applying here? And at best, they would send a file to the dossier to the computer science department. Look, we got this strange application. Maybe you guys are interested in him. But computer science had no questions and ended up, fortunately, hiring. So I would say there are some exceptions, but by and large, math departments do not consider TCS as a branch of mathematics. But really, I want to go deeper than that, beyond just what I call the sociological argument. I want to say, is it good for computer science to think of itself as a branch of mathematics? And that's where I kind of have somewhat of an issue. So my undergraduate degree actually was in, my major was physics. I was a physics major. If you look at physics, theoretical physics can be very, very mathematical. I mean, strict theory, deep mathematics. However, the expectation is that the theory would explain and predict the world. So you can do the math, you can be as abstract as you want. At the end, you have to explain and predict the world. If you don't do that, eventually the physicists will say, not a useful theory. String theory is controversial even among physicists. They're saying it's not testable, it's not falsifiable, it has the Popperian principle, they are controversial. Even about math itself, John von Neumann, prominent both theoretical and applied mathematician, talked about math. He said there's a great danger that without application, the subject, he meant math will develop along the line of least resistance. I mean, sometimes it is quotable that math is like water. There's no resistance, it flows in the direction of least resistance. Okay? And so I would argue that this theory should be inspired by theoretical physics. And what does it mean? It should explain and predict computing in the real world. Not just a theory, but it should predict and explain computing in the real world. And I want to examine one of the most outstanding problems from that particular lens. I want to examine P versus NP, which, at least in theoretical computer science, is the most outstanding open problem. In fact, this is the problem even mathematicians say it's a mathematical problem. At least, I don't know how many people in math departments working on it. Nevertheless, the Institute of Mathematics in 2000 declared a list of problems considered millennium problem, and P versus NP was one of them. $1 million prize. I'm not sure whether it adjusted for inflation or not, but $1 million prize. By the time we solve it, maybe it would be like a quarter. So let me talk a little bit, kind of assuming some broad audience here. Excuse me if I'm going over materially or no. I'll go a little bit to explain P versus NP. So it focuses on computational problem, and I'll start with a very natural graph theoretic problem. So given a graph, a set of nodes and a set of edges between them. And two questions that seem to be very similar. One is Hamiltonian cycle. Is there a path that visits every node exactly once? And Eulerian cycle, is there a path that visits every edge exactly once? Is there a cycle that visits every edge exactly once? And given a graph, how hard it is to find Hamiltonian cycles, how hard it is to find Eulerian cycles. Now, the Eulerian cycle in particular is a very important problem because, first of all, my understanding is the beginning of graph theory. So now we are in 18th century Königsburg, and which at the time was part of Prussia. Today it's Kaliningrad, which is part of Drop the P, and it's part of Prussia. And this is a map, the hand-drawn map, and you see that there is a river with an island in between, and there are 7 bridges. And on Sunday afternoon, the burghers, the citizens of Königsburg like to take a walk, and which people ask, can you take a walk, cross every bridge exactly once, and end up where you started? And they couldn't figure out whether they do it. So they said, well, we have a famous mathematician, Leonard Euler, and he did what mathematicians are supposed to do, abstract the problem. He said every contiguous piece of land is really essentially one node. The bridges are edges, you get this particular graph. Another question is that this graph has an Eulerian cycle, a cycle that visits every edge exactly once. Now, Hamiltonian cycle, the problem came from a very specific puzzle. There was this very specific graph, and the puzzle was construct a path that visits every node exactly once. It's a non-trivial path, but then it would generalize to ask about general graph. Do they have Hamiltonian cycle? Now, computational complexity asks how many Turing machine operations, but you can think of it how many any machine will do. How many basic machine operations does it take to solve a problem of size n? When you take a graph, the size will be the number of nodes plus the number of edges. And we're interested in scaling behavior, not just does it run in 2 minutes, but how many operations, and how the number of operations scale as the graph gets larger and larger. And we want it to scale in a polynomial entropy system for some fixed C. This is considered somehow feasible. Of course, if you take C to be 100, it's not so feasible, but let's stay with this abstraction right now, this polynomial time. Now, many problems are in polynomial time. Is a given graph, a given number even, just check this significant bit. Is a number square in polynomial time? Well, if you know how to extract roots, what's called long-hand extraction of roots, go back to, I don't know how many people still remember how to do it by hand, but you can go visit the algorithm and see polynomial time algorithm.
You could do binary search.
Hmm?
You could do binary search.
You can do a binary search, but that's more sophisticated. And I like long-hand extraction of roots. It's a test of age. I don't think they teach it anymore. Does the graph have Eulerian cycle? So the answer is the Euler proof. It's a fairly easy theorem that the Eulerian cycle, if and only if every node has a given degree, because you have to enter and leave, and you can show that this is if and only if, and we can see immediately that this graph does not have the Eulerian cycle. So the answer is to this. Can you take this nice afternoon walk? The answer is no. What about Hamiltonian cycle? Can we do this in polynomial time? Now, you can do naive algorithm. You should just try all permutation. There will be n factorial. You say, no, I learned computer science. There's something called dynamic programming. I'll start composing Hamiltonian path and combine them. Then you can then do it in 2 to the n. But if you give a graph of 200 nodes, not a very large graph, the universe is younger than 2 to the 200 Planck time units. So Planck time unit is 10 to the minus 35, if I remember correctly. So this is the question, very simple problem, can we do better? And in fact, this problem is so simple that people keep coming up with polynomial time algorithm for it. It's one of the most often solved problems to prove that P equal and P. But then another amazing observation came up in the early 70s that in this case, checking is easy. If I give you if I say, here is my solution, you can check that you visit all the nodes exactly once, and you always go between them crossing an edge. So easy to check. Clearly, in fact, it's going to be linear time. And so NP is the class of problem that can be checked, solution can be checked in polynomial time. And there are many such problems, again, factoring numbers. If I give you, 2 factors, you multiply, you see if it's a factorization. Finding the factors seems to be more difficult. Turns out tens of thousands of problems all over the place have this feature that it's easy to check. We don't necessarily know how to solve. So that's the class NP. So essentially, what P versus NP ask, and as far as we know, in fact, Gödel was the first one to raise the question about coming up with a proof versus checking a proof, is discovery of solution and check of solution, are they the same or not? The intuition is that, yeah, sure, checking should be easier. Intuitively, we think checking should be easier. We have a metaphor, finding a needle in a haystack. Nobody ever talked about checking whether this is the needle. Just stick your finger, get pricked, this is the needle. Pseudocode is easy to check, mathematical proof, depending on who wrote the proof, but still we understand it's easier than coming up with the proof, right? We look at some proof and say, wow, how did they come up with this idea? Okay. I was, before coming to ICE, I was at IBM Almaden Research Center, and the director of the lab was a physicist, and I was department manager. And one day, somebody from one of the researchers who was on staff with the director came and said, director, has a question. What is the question? He said, generally, you guys believe that P is different than NP. I said, yeah. So why don't you just accept it and move on? Which is what physicists do, right? There's no evidence of the contrary, so accept it and move on. Now I have to explain, well, we don't know how to prove it. And we don't know how to prove it. It means we don't really understand it. So that was satisfactory answer. We don't know how to prove it. I think it was Hamming said that the purpose of a proof is insight. I believe it was Hamming. On top of defining NP, we define NP complete problem, which are the hardest problem in NP. And in 1972, Carl proved that the Hamilton cycle is NP complete. So now we understand why people keep attacking this problem, because if you prove it's a polynomial time, then P equal NP. If you prove it's not a polynomial time, it's different than NP. And by now there are thousands of NP complete problems, and you can try to attack any one of them. So is it possible that P equal NP, even though everybody believes that P? So Scott Aronson wrote about this very poetically. I like to quote him. He said, if P equal NP, then the world would be a profoundly different place than it used to me to be. There will be no special value in creative leap, no fundamental gap between solving a problem and finding a solution once it is found. Everyone who would appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. So the general common belief is P is different than it. But I want to talk about, I fully accept this is one of the most fundamental problems in theoretical computer science.
But do you accept the sentences that Scott wrote? Because it is nonsense, right? I mean, suppose P is equal to NP, but there are algorithms that work in time n to the 100.
This is my next slide. Thank you very much.
Okay.
Great mind takes a lot. So now I want to talk of P versus NP in practice. So I think that I agree with Noga that Scott seemed to really interpret it that if P equal NP, then NP is easy, okay? Or if P is different than NP, that means that NP is hard. But when I was a freshman in physics, and we had a TA who was a PhD student, and at that point we thought the PhD students are all geniuses because we are just freshman students. And the TA asked us what the difference between theory and practice. And nobody could come with a good answer, and then he said, in theory they're not very different, but in practice are quite different. So P versus NP is a theoretical problem. We should not confuse it with practice. Okay? Why? Because you could have, as Noga just pointed out, we could have P equal to NP, but I was even more pessimistic than you. I said n to the 1,000. You're willing to go n to the 100. I said, suppose it's n to the 1,000. Useless as an algorithm. In fact, I would say if you look at our polynomial algorithm, you see that unless it's a small degree polynomial, it's not practical. I have some experiment on n to the 7 algorithm. Doesn't take much, take on input n equal 100, it's already, 10 to the 14. So really in practice, only low degree polynomial, maybe cube are practical, beyond that, no. The other possibility is that NP is different than NP, but you can capture all of NP in n to the log n. Okay? So if you take, for example, the age of the universe in Planck time units, and you do log, it's about 3. Base 2, not even base 10, log 2. It's about 3. So if you can simulate all of NP in n to the log n, wow, this is fantastic. Of course, depending on the constant, okay? Maybe there is a hidden constant there that is astronomical. So we should not confuse the theoretical problem with the practical problem. They are quite different. And that's where I start talking about the difference between thinking about it mathematically or being inspired by physics and thinking, what does it mean for real computation? But I want to go deeper and take the first NP-complete problem, the very first, as defined by, as proved by Cook, and this is Boolean satisfiability. So Boolean satisfiability of a Boolean expression, the variables are 0 or 1, true or false, and we have conjunction, disjunction, and negation. And you can think we have an expression, in this case, not x1 or x2 or x3, and not x2 or not x3 or x4, and x3 or x1 or x4. And is there an assignment such that when you do Boolean evaluation, you get 1? This is Boolean satisfiability. And that was the first NP-complete problem. So, in fact, it has a celebrated history. The history goes back to the 19th century. You find already William Stanley Gibbons, who is the follower of Boole, and he wrote, I've given much attention therefore to lessening of the manual and the mental labor of the process, and shall describe several devices which may be adopted for setting out the risk of mistake. In fact, the first logic machine was the shape of a piano, for the logic piano. There's some museum in England. It could solve problem with 4 propositions. 4 proposition assignments. But this was, if you still can do it with moving wooden pieces, go for it. Not so simple. To me, more amazing is the quote of quoting Ernest Schroeder, was German algebraist and logicians, getting a handle on the consequences of any premises, logical premises, or at least the fastest method for obtaining these consequences, seems to me to be the noblest, if not the ultimate goal of mathematics and logic. Wow. So you're working on start solving the ultimate goal of mathematics and logic. I think that's ambitious than that, right? And then people did not make progress. There was some progress, but theoretically was finally Cook in 71 and Levin in 73, both proved the Boolean satisfiability is NP complete. And it's the first problem for NP complete because it's the easiest to use it to encode non-deterministic polynomial computer machines. But people have been working also on the practical side of it, actually solving this algorithmic Boolean reasoning. And the first solver that I know of was developed by Newell, Shaw, and Simon already in mid-50s, 1955. They call it logic theories, and they were able to prove mechanically all the theorems in positional logic for Principia Mathematica. The most systematic way is a paper that was classified for many years because it was written in the technical work done for the National Security Agency that does signal intelligence by Davis and Putnam, computational method and positional calculus. Then Davis and Putnam published a paper in 1960, and then follow-up paper in 1962 by David Logeman and Loveland. And that gave rise, combining these two papers, gave rise to what we call today DPLL, which is essentially backtracking search. But it's backtracking search with one, convert the formula to conjunctive normal form. This formula is conjunctive normal form because it's a conjunction or disjunction, and negation is only applied to variables. And we know how to convert all formula to conjunctive normal form. Then we do backtracking search, but there is one really heuristic that is very, very important, as I'll talk more about it. If when you look, so one of the issues is you have to find a variable to branch. But imagine that the first clause here would be just not x1. Because it's a conjunction, at this point there's no more choice. You have to make x1 false. So this would be called a unit clause, and you should identify unit clauses and pursue them vigorously. So this was DPLA. And I would say is from 63, almost for the next 30 years, very little progress was done about the practice of Boolean satisfiability solving. When I was a PhD student, you could solve problems with maybe hundreds of variables. If you want to do more, say, what do you want? It's a bit complete. What do you expect us to do? Magic. And then there was so-called the Sutter evolution. And he started with a paper in 1996 by Joao Marquez Silva and Karen Sakala. The tool was called GRASP. That's the title of the paper, GRASP, the algorithm for satisfiability. And this is a quote from the abstract. The paper introduces GRASP, genetic search algorithm for the satisfiability problem, a new search algorithm. Its most distinguished feature is the augmentation of basic breakpoint search with powerful conflict analysis procedure. I'll explain in a few minutes what does it mean. The second important paper was done here at Princeton by Shard and his students in 2001. Shard, engineering inefficient subsolver. Why Shard?
Students get to pick.
Hmm?
Students get to pick.
The student gets to pick. Okay. But why? What Shard? That was an acronym.
No acronym.
No acronym. Okay. And again, here is a quote. In this paper, we describe the development of a new complete solver, SHAP, which achieves significant performance gains with careful engineering of all aspects of the search, especially and particularly efficient procedure of Boolean constant propagation, which is the same term as unit propagation. And a new low overhead decision strategy. And I'll explain all these terms in a minute. And this paper gave rise to a new, we used to have DPLL solver for about 40 years. And I said 2001 was the year where we went to a new generation or new type of technology, what we call today CDCL solver, or conflict-driven closed learning. And unfortunately, I think this was a historical mistake, call it CDCL, because it sounds like completely technical and not interesting. Suppose I had called it deep solving. What would have happened there? So I'm trying to summarize it as 5 key heuristics. There are more heuristics around. It's today, solvers are very sophisticated software tools, but I describe the five key heuristics that enable us to scale to millions of variables. Okay, so this empirical problem, we solve instances with millions of variables. So let's go, what are these 5 key heuristics? So you're familiar with backtracking. The search failed, you go one level up, you go one level up. But already in 1977, a proposal was made to do back jumping. When you fail, try to figure out what is the highest level you can go to continue. Don't just go one by one, do some analysis and jump higher if you can. Okay? And here you have to distinguish between the variable that you don't know what to do. You have to decide assign equals 0 and 1, and variables that whose value is determined by unit clauses, by Boolean constant propagation. So do back jumping. And this requires that you build a graph, analyze conflicts, but it's an important point. The second one is PCP. So observation that the one thing that very radical thing that Chara did in his work with the student was, let's do profiling of what the code actually does. It turned out it spent most of the time on PCP. Up to 80% of the time, if I remember correctly. And so now the naive way of identifying unit clauses is to keep a counter next to every clause of how many variables are unassigned. And when it gets to B1, you know it's a unit clause. But that means that when you make a choice, you assign a variable, you have to update the counters. And then when you backtrack or backjump, you also have to update the counter. So again, it turns out you spend lots of time updating counters. And so the paper came up with a very, very original technique. That's why I said it's creative leap. We talked before about creative leap. With creative leap, instead of keeping counter, having pointer to 2 unassigned literals. And at some point they have to clash, and then you know you have a unit clause. So it's a very simple test. Unit clause does not require updating counters so often. The one introduced earlier in the 1996 paper was closed learning. So suppose the search failed. You did an assignment and you got false. You said this assignment is bad. I should block it. How do you block it? You add, if the assignment was, you use literal as P or not P, they're assigned by a vector of literals. You negate, you can think of it as a conjunction, negate, you get a disjunction. It's a clause. You add it and you block that particular assignment. But if you do it just naively, you end up with very long clauses. And very long clauses are bad because it will take a long time before they become unit clauses. You want to add short clauses. So they said, let's go back to the implication graph and do clever analysis to find out what are the shortest possible conflict we can identify, and add that as a learning clause. And in fact, we can show that this corresponds to resolution of clauses. And resolution really was the idea by Davis Putnam in the first paper in 1960 was all about resolution. Resolution is searching for a refutation. So what we're having today, essentially solvers do bidirectional search. They are both searching for a solution, but at the same time they're searching for refutation. Because they're trying to say a formula is satisfiable or not. If it's unsatisfiable, we want a proof. So now we are having and other thing that happened between 1958 and then 1996. 1958, memories were small. One second, memories were small. And by the mid-90s, memories were large. You could remember lots of clauses. The problem they had already in 1950, the reason we went from resolution to search, because the resolution you have lots of clauses, and memories were small. Yes.
So there must be a way to generate these kind of formulas that are hard for all the software, even with hundreds of.
Yes, I'll come back. Yes.
So do we have a good understanding of how to?
I'll come back to it. Keep this question. The final heuristic here, or not the final, one more heuristic is how to choose variable. You need to choose a variable to split on. And I think it was in Indiana Jones and the Last Crusade, where they have to choose between the chalice, which chalice to drink from, and answer, and the advice is choose wisely. And so you want to choose which variable to split on. So people thought, well, we should choose the variable to minimize the search. That's good advice. Except if you take it too long to make the choice of paying a penalty. So it turns out if I use the Superman metaphors, Superman has enemies. One of them is Brainiac. Brainiac is smarter than Superman. Speed Demon is faster than Superman. But Superman is just the right combination of smartness and speed, so he can defeat this opponent. This is the same here. We can choose very wisely, but there will be a lot of overhead because of decision time. Or we can choose quickly, but then we're not minimizing the search time. So you need the heuristic that will balance the two, and that was another contribution of the 2001 Princeton paper, to come up with a particular heuristic that we should look at variables that participate in conflicts. They seem to be important variables, and this is called now visits, and that was the right compromise between Brainiac and the speed demon. Other heuristics are, when things go tough, just restart. You've done a search, you went up and down. At some point you say, you know what, let me restart. And when you start, you don't start from scratch because you have learned some clauses before. So when you restart the whole search, you have some new clauses you learn, and they block many assignments. So this is something that again, it was proposed independently in 1998 by Gomez, Selman, and Kautz. And now you have the question, how much do we start? And some solvers that do aggressively starting. About every 50 backtracks just say, you know what, just not working, let's restart. And so this, I would say, to me, these are the 5 key heuristics of CDCL solvers, or deep solvers. And how effective they are. I think this is a 2012 slide by Sandeep Cheshire. But we did, he wanted to assess progress over a decade. So he took 10 years more than 10 years, like 12 years of such solvers, ran them on the same benchmark on the same machine. As people publish the papers over a decade, they were different machines. Ran them all on the same machine so we can actually compare and show how on this benchmark he got improvement from 800 seconds to 1 second. So 3 orders of magnitude of improvement. And such solvers are still getting better, so much so that people are talking about Moore's law for such solvers. They just keep better and better. And they have gotten so much better, already by 2012, people at Microsoft start saying, can we use them in real life, not just in academia, and we use them for Microsoft software development. And the paper was published in 2012 by Demura and Bjorner, showing how Microsoft is using them for actual software development. And as we speak now, there are hundreds of machines in Microsoft in the cluster churning and solving such problems. And I want to talk about one application for hardware engineering that's based on such solver, because I think I want to show you again the importance of the difference between what is true in theory and what works in practice. So the problem I've been working on for many years was verification of hardware systems. But in general, this is true. Anybody who has written programs, the writing program is the easy part. Getting it to work is the hard part. And this is true in general for people who develop systems. They tell you the estimated industry is that verification takes 70% of the effort. So twice as much you spend on verifying the code and debugging it than writing the code initially. Now, I've spent my career working on mostly on formal verification, where you write formal properties and you develop essentially mathematical proofs that the software or the hardware satisfy this code. When you go to industry and you try to get an estimate how much they spend on it, it comes up to about 10%. You look at number of people who do formal, number of people who don't do formal, it's about 10%. What do the others do? What you do when you write software, you test it. So this has developed now into if there is a good methodology, but this is really what the industry does. You take the system, hardware, software, you run well-chosen test cases only, and you let them then, you run them, you see if you get the right result, that's how you debug it. Classical bug, one of the most famous bug, was the Pentium couldn't do floating point division correctly. So how could we test floating point division? Well, the problem we have is the test space that is huge, right? Two numbers of 128 bits, 2 to the 56. Again, it's more than the Planck time unit since the Big Bang. So we have to choose wisely. We have to test wisely. So what people used to do is the testers or verification engineers that are called would pour over the requirements and identify corner cases and write tests, explicit tests. And the conventional wisdom was that writing tests is like writing code. Software engineer writes about 20 lines of code per day. So it turns out that doing this was not scalable. You needed lots of testing, and you had army of testers. So a methodology developing IBM research in Israel in the mid-90s, which is instead of writing explicit tests, write method tests, right? Constraint describing a scenario. And then use a constraint solver to actually come up with concrete values, and then run this test. So in this case, and you can run many tests, generate many tests like this. And this has become now the dominant approach in industry. But if you just write constraint or give it to a constraint solver, the solution you get depends on the internal of the solver. You know nothing about what kind of test you get. So really, people said, well, what we really want is for the solver to generate random assignment, random solutions. And because we know nothing about it, they should be uniform. We don't want to be stuck to one corner of the test space. So the problem that emerged from that was given a Boolean formula, a sub-instant, generate solutions uniformly at random. We want to be scalable to industrial size problems. So I became aware of this problem in 2006. I heard a talk by people from IBM Research describing this methodology. So I went and studied the theory of this, and it turned out that I call it constraint sampling, and this is, people studied this already in the 1980s. There was a paper by Jerome Valiant and Basirani, and they show you can do it in BPP, which is a randomized polynomial algorithm, with an oracle in sigma P2, second level of polynomial hierarchy. And then in 2000, Bellard, Goldwasser, and Petran show you can do it in BPP to the NP. That means you can use such solver as an oracle, so you have a randomized polynomial algorithm with the such solver. You can run it. So in 2011, Kuldeep Mill was ungalvanized and came to me, took my logic course, wanted to do research. I said, let's start with implementing this algorithm. So we implement algorithm in its scale to n equals 16. 17 in timed out, we couldn't get it to finish. Kuldeep thought this was great. He wanted to submit a paper. And I said, look, we have such solvers today solving millions of variables. If we submit n equals 16, the review would say, ha, ha, ha. That's it, nothing more. Said, it doesn't scale. We have to find a way to scale it. So what we had to do, we go back to the drawing board and developing new theory. Once we learn about the practice, we have to get better theory. And that was together with collaborators, Pratik Chakraborty, Daniel Fermont, Sanjit Cheshire, and we show that you can get almost uniform generation in BPP to the NP, but it scales.
Can I ask a couple questions?
Yeah.
So what benchmarks would you use here? Like when you were saying that it breaks at n equals 17, what are the benchmarks?
There are lots of benchmarks for satisfiability. So we just took this benchmark and said, let's try to generate.
But how would you know that you are sampling randomly or not? How are you?
I'll talk a little more about it, okay? So, and we have to develop better theory, but also use some old theory and some new technology. The old theory was universal hashing, and the new theory was SMT solving. So, one is we compromise on the uniformity. We said it's not to be almost uniform. What does it mean to be almost uniform? If you have kappa solution, uniformity would be every solution which will be 1 over kappa. We said You choose an epsilon, which is your required accuracy, and approximate to the factor of 1 plus epsilon. So it's almost uniform. And of course, you can choose epsilon. The smaller epsilon will be, you're going to pay a penalty. You want something will be polynomial in 1 over epsilon. So this is almost uniform. So what is the idea? The idea is, remember, we have this large space that we know nothing about. The idea is to somehow carve it into smaller cells. The cells will be small enough that we can enumerate the solution in a cell. And then we choose, if I have a body solution, I know how to choose perfect randomness. Okay? So, but the challenge is, how do we take an unknown space and carve it into roughly equal, almost equal cells? And the idea is to use universal hashing. Again, idea that came clearly from the theory community. And the idea was, if you go back to like the art of computer programming and you read about hash function, the idea is to choose a hash function that will be good. So if you give it roughly well-distributed input, it will generate well-distributed output. But we don't know that our inputs are well-distributed. Okay, so we have to try to we want a hash function that will, whatever is the input, it will generate well-distributed outputs. And here comes the idea of universal family of hash function, which is you randomize the choice of hash function as we overcome the unknown nature of the distribution. There's also issue of strong universality, which I'm going to skip for now, but that's apparently was the key. So if you look at BGP, they require the technical reason they require high level of strong universality, and it was completely expensive. We gave them uniform distribution. We compromised. We went to a low degree of universality, but it gave us almost uniformity. But that was the key to scaling it from tens of variables to millions of variables. And how do we partition an unknown distribution into nice cells? We had random XOR constraints. You take a random sum of variables, you choose the variable with probability half, you check a random sum, XOR sum of variables, and you can see that every such XOR constraint splits the solution space in two. So if I choose m of them, I will split it into 2 to the m cells. If I choose enough of them, the cells will be small. But now I have to solve problems that are a combination of CNF and XORs.
The XORs are long clauses now, right? Like
At this point, they are long, and there's been a line of research how to make them short. But I won't be able to talk about it today. So it turns out that if you can take XOR constraints and you convert them to CNF. If you do that, you kill the SAS solver. They're not going to do it. So we were trying to figure out how to solve this combination. And it turns out that since 2000, people have explored how to combine SAS solving with other types of solving. XOR concerns by themselves are easy to solve. The linear equations modulo 2. You all know how to do it, just Gaussian elimination. How to combine the two, the technology was developed since 2000, and we stumbled on a solver developed by mathematicians called Cryptominisat, which was just what we needed. So we are just very lucky. It was there for us to use. And how do we test uniformity? For example, we chose a problem that had like million solutions. We implemented a uniform sampler. For a million solutions, you can number them, and you can implement a uniform sampler. And then there are ways we try to we choose the histogram of occurrences, and statistically it turns out that our almost uniform sampler is indistinguishable from a uniform sampler.
So these are benchmarks where you know all the solutions.
These are some benchmarks. Million solution we can enumerate. Okay, a billion solution we could not enumerate. So a million solution we can implement a uniform sampler. And we benchmark ourselves against the best sampler of the time. There was XOR sample prime, which was no guarantee of uniformity, almost uniformity, just best effort. And we are still faster by orders of 2 or 3 orders of magnitude. So let me try to kind of wrap up. So how did we get this good performance? By first of all recognizing that the current theory was very nice. There was a nice algorithm that didn't work in practice. This forced us to go back and redo the theory. So let's just a little reflection on NP completeness. So when I was a PhD student, NP was hard. You have nothing you could do. You could just lie on the ground and whimper. And there's nothing you can do. And NP is hard. That is to say, someone mentioned here, we can synthetically generate such instances with a few hundred variables that no such solver can solve.
I think they can really be just random instances. 1,000 variables.
Particular type of random. No, not particular type
Uniformly
of random.
random. Uniformly random.
Not enough. Particularly type of random. Particular, some random problems are easy. No, some random problems are easy. Particular type of random are hard.
Moshe, they're not. I can discuss this, but
Okay, let's discuss it later. But for some reason, there's something magical about industrial problems. They're not random, they're very not random.
Yeah.
They describe human artifacts. There's something, we don't know what it is about it, but there we can actually solve very large problems. What does it mean? It means the theory that we have is not rich enough. It doesn't, with complexity theory, the goal is to tell us what is easy and what is hard. We know that some can be hard and some can be easy. We don't have a good theory to explain it. So this is, I remember talking to a cosmologist some years ago, and I said, cosmology is in crisis. He said, yes, but also an opportunity. So I think something here. So let me paraphrase von Neumann. There is a great danger that TCS will develop along the lines of least resistance. It should explain and predict the real-world computing. Not every paper. Okay, I'm not expecting every paper to say, here is how the experiment I ran, but we could step back and to say, okay, that's the theory, for example. I'm looking at NP completeness, beautiful theory. Does it explain real problem life solving? And I said, no, there is a gap. We need better theory. And if we do that, we get better theory and better practice. But the other point is that such solvers today are like hammers. When you have a hammer, what do? You go hunting for nails. Go look for nails. And to wrap up, I published a column in CSCM, for theoretical computer science. That was in October of last year. And preparing this talk, I went back to Wikipedia. And somebody has changed it now. I'm not a mathematician anymore. There's an Israeli theoretical computer scientist. I still have issue with that. I don't think it's quite correct. I'm very real. I'm a computer science theorist, not a theoretical computer scientist. I'm a real computer science theorist. Thank you very much. Yes.
So regarding your conclusion, I wanted to ask the following. So I understand like this question about experimentation not being like a fair amount of standard in theoretical papers, but NP completeness is a extremely coarse theory. I think we understood this even back in the 80s, that this is the first cut theory. And since then, there have been many attempts at like beyond worst case theory. Like there's a theory of random SAT, there's a theory of smooth k-SAT formulas. So you're right that NP completeness maybe does not shed as much light on SAT solving as you would want. But there are lots of like better models for input instances.
What are better models you have in mind?
So I'm saying that there is theoretical work on other models of SAT, which go beyond like the worst case modeling. And I wanted to say, what your opinion was like,
So I'll give you an example. So there was a paper in the early 90s, famous paper, where the hard problems are. And they look at random SAT problem. And I realized the critical parameter that both Noga and I had in mind, I think, which is what's called the density of the problem, the relationship number of clauses of the number of elements. And they pointed out that for a sparse problem are easy. You run solve on them and you solve them in polynomial
So just to clarify, you're looking at the regime where the formula is satisfiable now?
Formula are satisfiable probabilistically.
Yes, but like you're looking at
the still unsatisfiable formula, but the point is such solver will converge quickly. Okay.
So just in the unsat regime or the SAT regime?
At the low density. That's the satisfiable regime.
Okay, good.
Okay. Then as the formula gets denser, there is a magical point. We don't have a completely tight proof, but there is a magical point that at density 1.426, who knows how many digits, its probability is high. Yeah, we have.
You're talking about k equals 3 now. 3 SAT.
Yeah,
You're talking
yes,
about
three
three
sub, three
subs,
sub.
yeah.
Yeah, depends on, generally depends on case, it depends on the position, depends on case. And then they claim that it after that becomes easy. So they call it the easy hard easy pattern, and they say, well, the hard problems are in the phase transition. But today we actually understand it better. So one is a low density is easy, up to roughly density 3.8. Around density 3.8, the formula are still satisfiable, but they suddenly become hard. And they stay hard after that. Even high density problem, unsat formulas are low bound. They're exponentially hard, except the exponent declines. They're still exponentially hard, they're still C to the n, but C becomes smaller. So we have a better understanding for this very specific model. Okay, which everybody understands today, very synthetic and does not describe real life formula. Okay, we have a better understanding. They're not complete, but we have better understanding. Okay, but for such in the real world where it's being used, we are way short of having an understanding what's going on. Yeah.
Can you explain what density is in this context?
What's what?
Density? You just
I
have.
said density is the ratio of closest to variables.
Okay.
Okay. How many clauses you have? Is the problem under constraints? You imagine density is 0, you have no clauses. So it's always satisfiable. The more clauses you add, the more constraint, how constrained the problem can be under constraint or over constrained, essentially. Okay, that's density. Yes.
An objection to an example that may not be of theoretical interest, but is practically important. The Pentium bug would actually have been found by a human written unit test. I'm biased, I write human.
So once people figure out what the bug was, then they figure out how they could have found it. This is true. Okay.
That too is my
Yeah.
job, but.
Yeah,
but
and that it was incorrect entry in the table, okay? It was, but yeah, it could have been found. So industry is using such solvers today as a standard working horse down industry, okay? There's no question about it.
But they're not using enough of these sort of tests that would have found proper unit tests for.
That I can tell you, maybe you're right, how much they're using, I don't know. Yeah. Okay.
Thank you very much.